Hello! In this video, we're going to look at some example problems involving proofwriting. And these examples are going to involve logic. So pretty much, they're going to involve statements which we just represent as letters P and Q. And if we see something that says this is read as not P. And if we see something like this, P with a right arrow to a Q, this means if P, then Q. So, now let's look at some example problems. These example problems that we're going to be looking at come from Daniel Velleman's book, How to Prove It. Here is our first example problem that we're going to do. Suppose if P, then Q, and if Q, then R. Prove if P, then R. So, we're trying to prove a conditional statement. When we're trying to prove a conditional statement, the first thing we could try is, if we make the assumption that P is true, can we logically deduce that R is true? So that's the technique we're going to try first. So for our scratch work, our first technique we're going to try is we're going to make the assumption that P is true, and we're going to see if we can logically deduce that R must then be true. So, let's see. Let's write down the other things that we're given. We're given if P is true, then Q is true. If Q is true, then R is true. Let's try to logically deduce that R is true. Now, we know P is true. We also know if P is true, then Q is true. So, the way we can read this is, whenever we know that P is true, we can conclude that Q must then be true. Well, we know that P is true, right? We're making that assumption, so we can conclude that Q must then be true. So, from the fact that P is true, and from the fact if P is true, then Q is true, these two statements tell us that we can conclude that Q must then be true. This inference rule is called modus ponens. So, we now know that Q is true, but we also know if Q is true, then R is true. So we apply modus ponens again. Since Q is true, and we know if Q is true, then R is true, we can conclude that R must then be true. So we've logically deduced that R is true, which is exactly what we wanted. So what we've done here is, we have proven, under the assumption that P is true, we can logically deduce that R is true. So we've proven, if P is true, then R is true. So, as you can see, we have a proof. So, let's get into writing it up. So, we're trying to prove this statement. We're trying to prove if P is true, then R is true. And the way we're going to do it is we're going to make the assumption that P is true, and we're going to logically deduce that R is true. So, we will assume P, and from here we will logically deduce that R is true, following what we did in our scratch work. So pretty much, what we noticed here was, since P is true, and if P is true, then Q is true, we can conclude that Q must then be true. And then the next thing we noticed was, since Q is true, and if Q is true, then R is true, we can conclude that R is true. And so we have logically deduced that R is true. So, what we've shown here is, under the assumption that P is true, it follows that R is true. So, that proves, if P is true, then R is true. So we can write, therefore, if P, then R. So that's it. This completes the proof. So now let's look at another example problem. Suppose if not R, then if P, then not Q. Prove if P, then if Q, then R. So our whole goal, once again, is to prove a conditional statement. right? The conditional statement that we're proving is if P is true, then if Q, then R is true, right? That's the overall conditional statement that we're proving. And again, we're going to use the standard technique. Let's see. If we make the assumption that P is true, can we logically deduce if Q, then R is true? So for our scratch work, to prove this statement, we'll make the assumption that P is true. And from here, we will try to logically deduce if Q is true, then R is true. So we're trying to prove if Q is true, then R is true. So we're trying to prove a conditional statement once again. And so the technique we could try to prove this is if we make the assumption that Q is true, can we logically deduce that R is true? So to prove this, let's make the assumption that Q is true. Let's try to logically deduce that R is true. So what can we do? Well, let's notice the first statement that we're given. Can we really do anything with this? All right, we're given P, Q, and this statement. Can we do anything from that? Well, if you can't see anything right away, maybe we should try a different technique to demonstrate if Q is true, then R is true. One technique is we could try to prove the contrapositive of the statement, right? The contrapositive tells us that if Q, then R is equivalent to saying if not R, then not Q. Right, so let's take a step back. So to prove if Q is true, then R is true, we're going to try to prove its contrapositive. What the contrapositive is it is the statement if not R, then not Q. These two statements are logically equivalent. So these two statements right here are logically equivalent. So if we can demonstrate that this statement is true, then that tells us that this statement must be true. So let's try to prove that this statement is true. To prove this statement, we'll make the assumption that not R is true, and we'll try to logically deduce that not Q is true. So let's make the assumption that not R is true, and we'll try to logically deduce that not Q is true. So let's see if we can do that. Well, looking at the other thing we're given, since we know not R is true, and we also know if not R is true, then this statement is true, we can apply modus ponens. So, since we have not R, and we have if not R, then this statement is true. We apply modus ponens here to conclude that this statement is true. We have if P is true, then not Q is true. So we can conclude that this statement is true. But next, we know that P is true, and we also know if P is true, then not Q is true. So we can apply modus ponens again, right? We know P is true, we know if P is true, then not Q is true. So applying modus ponens here, we can conclude that not Q is true. So that's it. What we see here is, under the assumption that not R is true, we can logically deduce that not Q is true. Therefore, we have demonstrated if not R is true, then not Q is true. So we've proven that this statement is true. But since these statements are logically equivalent, that implies we must have that this statement is true. If Q, then R. So, now let's put this all together. Our whole goal has been to try and prove this statement, right? And the way we did that was we made the assumption that P is true, but we've just logically deduced if Q is true, then R is true. So that proves our entire statement. So we're ready to write up the proof now. So, going to our proof. Remember, the whole goal was to prove this statement. And the way we did that was we made the assumption that P is true. So that's the first thing we're going to write in our proof. Assume P. From here, we are going to logically deduce that if Q is true, then R is true. The way we did that in our scratch work was we proved the contrapositive of that statement. So what we're going to write down in our proof is we're going to say to prove if Q then R, we are going to prove the contrapositive. Right? And this indicates that we're going to prove this statement instead. And the way we did that was we make the assumption that not R is true. So we're going to say, so assume not R. From here, we're going to logically deduce that not Q is true. So following what we did in our scratch work, since we know not R is true, and if not R is true, then this statement is true, that allowed us to conclude that this statement is true. And then the next thing, since P is true, and if P is true, then not Q is true, that allows us to conclude that not Q is true. And so what we've done here is, we have shown, under the assumption that not R is true, we can logically deduce that not Q is true. Therefore, if not R is true, then not Q is true. But, remember, this statement was logically equivalent to saying if Q is true, then R is true, because we're proving the contrapositive of it. So what we're going to say here is, because we know that this is true, we can say if Q is true, then R is true. So we've demonstrated that this is true. So now, putting this all together, we see under the assumption that P is true, we have logically deduced if Q is true, then R is true, which means we have proven this conditional statement. So we can say, therefore, if P, then if Q, then R. So this completes the proof. All right, so now let's look at another example. Suppose if P, then Q, and if R, then not Q. Prove if P, then not R. So, we're trying to prove a conditional statement. So the standard technique is, let's make the assumption that P is true. Let's try to logically deduce that not R is true. So for our scratch work, we'll start out by making the assumption that P is true. We'll try to logically deduce that not R is true. So, let's see. Can we logically deduce that not R is true? Well, let's write down the other things that we're given. So, we're given if P is true, then Q is true. If R is true, then not Q is true. So, we see that P is true. We also see if P is true, then Q is true. So we can apply modus ponens here. So these two statements allow us to conclude that Q is true. Now, what can we do with this? We need to somehow deduce that not R is true. None of our premises contain not R in it. We don't have anything that says not R. We do have something that says R, however. Now here's the thing. Remember, this statement is equivalent to its contrapositive. The contrapositive tells us if this statement is false, then this statement is false. Or in other words, if Q, then not R. So, because we know if R, then not Q, this statement is equivalent to its contrapositive. So we can conclude if Q, then not R. So this statement is true, because remember, these two statements are logically equivalent. It's just the contrapositive. So we know that Q is true. We also know if Q is true, then not R is true. So we can conclude by modus ponens that not R is true. So from these two, we can conclude not R is true, which is exactly what we want. So what we've shown here is, under the assumption that P is true, we could logically deduce that not R is true. And that proves this conditional statement. So now let's write up proof. So we're proving if P, then not R. And the way we're doing that we're making the assumption that P is true, and we'll logically deduce that not R is true, following what we did in our scratch work. So, since we know that P is true, and we know if P is true, then Q is true, we used modus ponens to conclude that Q is true. The other thing that we observed was that this statement is equivalent to its contrapositive, so we can conclude that the contrapositive of this statement is true. So then, since Q is true, and if Q is true, then not R is true, we can conclude that not R is true by modus ponens. So, what we see here is, under the assumption that P is true, we've logically deduced that not R is true. Therefore, if P, then not R. And so this completes the proof. Okay, so now let's look at one more example problem. Suppose P is true. Prove if Q is true, then it is not the case that if Q is true, then not P is true. So, we're trying to prove a conditional statement. And so the standard way we try to prove it is we make the assumption that Q is true and try to logically deduce that this statement is true. So if we do make the assumption that Q is true, and our whole goal is to logically deduce the negation of this conditional statement, well, maybe that's not the way you want to do it, because we're trying to prove the negation of a conditional statement, and you might not be able to think of a standard way to do that. So let's try to prove the contrapositive of this. Right? The contrapositive tells us if this statement is false, then Q is false. Or in other words, if it is the case that if Q is true, then not P is true, then Q is false. So that's what the contrapositive tells us. So for our scratch work, we're going to be proving this statement. If we prove this statement, well, these two statements are equivalent, so that proves this statement. So let's prove this statement. And to do so, our standard technique is we assume that this statement is true, and we'll try to logically deduce that not Q is true. We make the assumption that this statement is true. So we will assume if Q is true, then not P is true. We'll try to logically deduce that not Q is true. Let's write down the other thing that we're given. Right? We're also given that P is true. So let's see, how do we logically deduce that not Q is true? Well, the thing to observe here is it's nice if we use the contrapositive of this statement. Since we know that this statement is true, well, this statement is equivalent to its contrapositive, so its contrapositive must be true. Right? The contrapositive of this statement tells us if not P is false, then Q is false. Or in other words, if P is true, then not Q is true. So this is saying that if P, then not Q. So this statement is true. But since we know P is true, and we know if P is true, then not Q is true, we use modus ponens to conclude not Q is true. So since P is true, if P is true, then not Q is true, we can conclude that not Q is true. And that's exactly what we want to deduce. So we have a proof, right? We can prove this statement. But since this statement is equivalent to this statement, that means we can prove this statement. So that's it. We're ready to write up the proof. So our whole goal is to prove this statement. And the way we're going to do so is we're going to prove its contrapositive. So let's write that down in the proof. Which means we're proving this statement. So the way we're doing that is we'll make the assumption that this statement is true. So assume if Q is true, then not P is true. The whole goal is to deduce that not Q is true. Now, the way we did that in our scratch work was we noticed that since this statement is true, well, that implies the contrapositive of this statement is true. Right? Every statement is equivalent to its contrapositive. So we can conclude if P is true, then not Q is true. But then, since we know that P is true, and since if P is true, then not Q is true, we can conclude that not Q is true by modus ponens. And that's exactly what we wanted to deduce. All right, so putting this together, what we've done here was, under the assumption that this statement is true, we've logically deduced that not Q is true. So what we're going to write is, we're going to write, therefore, if this statement is true, so if this statement is true, then not Q is true. So we've proven that this statement is true. Well, the technique that we're using here is proof by contrapositive. Since this statement is true, the contrapositive of this statement must be true. So in other words, because we've proven that this statement is true, we've proven that this statement is also true. right? Because these two statements are equivalent. And that is exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.